Now let us go back to the presentation and observe what happens when we titrate a weak acid and a strong base. Now a typical and in fact the most common example of a weak acid would be acetic acid or formic acid, and both are readily available, and a strong base would again be sodium hydroxide. So there are a few things that we need to consider or assume here. First of course is that the acid being weak, it undergoes minimal ionization, and another very important aspect that will become relevant when we are titrating a weak acid and a strong base are the concept of buffering that happens due to the presence of the salt and the acid in equilibrium during the titration. So this will induce slower decrease or increase in the pH, and so what we need to do now is to calculate the pH again at the pre-equivalence point, the equivalence point, and the post-equivalent points. So let us go back to the board and start doing some calculations. In this case, what we are doing is we are titrating again 25.00 ml of acetic acid, and its concentration is again 0.05 molar, just to make quick comparisons. So this we are titrating with sodium hydroxide of the same concentration, which is 0.05 molar. Now when we are titrating a weak acid and a strong base, we need to consider three different equilibria that may be in existence. The first one is the acetic acid undergoing dissociation into the acetate anion and releasing the hydronium ion. The second one is the reverse process, where the acetate ion, being a weak base, reacts with water and accepts its proton to convert back to acetic acid and generates hydroxyl ion. And the third equilibrium that may be of relevance again is the self dissociation of water. So these are the three equilibria that we need to consider, and we will also be considering the dissociation of acetic acid and the buffering action due to the acetic acid mixture present in the medium. Now with these points, let us try to calculate what are the pH values at different point on titration of acetic acid with sodium hydroxide. So first thing first is to calculate the initial pH. So before that, let us quickly write down the K value, which will be nothing but the dissociated form divided by the undissociated form of the acid, we also understand that if we look at the equation in the previous page, what we observe is that the acetic acid concentration will be reduced by undergoing dissociation in water to form the acetate, and it will be increased when the acetate takes up water and forms the acetic acid. And for each acetic acid that undergoes dissociation, we create a hydronium ion. For each acetate anion undergoing protonation, we create a hydroxyl anion. So, based on this, what we can say is that the concentration of acetic acid at equilibrium will be the initial concentration of acetic acid minus the hydronium ion concentration, because the hydronium ion is coming from the dissociation of acetic acid, plus the hydroxyl ion concentration, because the hydroxyl ion is coming from the reformation of the acetic acid from the acetate anion in equilibrium 2. Now, we also make a presumption that the dissociation of acetic acid is very less. So, the concentration of acetic acid that we begin with is much greater than either the hydronium ion concentration or the hydroxyl ion concentration. So, not much changes here, and what we believe is, or what we presume is, that the equilibrium concentration of acetic acid is similar to the original concentration of the acetic acid. So, another presumption that we have is that the hydronium ion concentration is equal to the acetate anion concentration, because acetic acid dissociation is going to be our key source of the hydronium ion in the medium. Now, when we plug in these into our equation 1, which is the acidity constant equation, what we observe is that Ka turns out to be equal to the hydronium ion concentration again into hydronium ion concentration divided by the original concentration of the acetic acid that was made. Now, when we reorganize this, this turns out that the hydronium ion concentration is nothing but square root of the dissociation constant into the concentration of the acetic acid that was originally taken. This is the equation that we can use to calculate the initial pH of the medium. So, let us go ahead and do that. Now, at this stage, it is also important to convey that the Ka value of acetic acid is known to be 1.75 into 10 power of minus 5. So, indeed it is a weakly dissociating acid. Now, with the Ka value and the concentration of acetic acid originally taken available to us, it would be straightforward to calculate what is the hydronium ion concentration of this medium. So, let us do that. What we observe is the hydronium ion concentration is equal to 1.75 into 10 power of minus 5, which is the K value, into Now, the concentration of the acetic acid that was taken originally, and this is 0.05 molar. When we solve this out, this turns out to be 8.75 into 10 power of minus 7 square root, and this ultimately solves out to be 9.35 into 10 power of minus 4 molar hydronium ion concentration. With this, it would be straightforward to calculate the pH, which will be negative log of 9.35 into 10 power of minus 4, and the pH of the medium now turns out to be 3.03. So, as we can observe here, when we are taking a weak acid, the initial pH is already 3.03 value, and now let us calculate, or let us see what is the pH value when we start adding the sodium hydroxide into this medium. So, let us take an example where we have added pH after addition of 20.0 ml of sodium hydroxide, which was again 0.05 molar. So, we need to calculate what is the pH of the medium at this stage. So, what we need to consider is the following, that sodium hydroxide, being a strong base, will react in a stoichiometric amount with the acetic acid and convert it into an acetate anion and sodium ions and water. Sodium hydroxide addition will convert acetic acid into acetate anions. So, let us calculate now the concentration of acetic acid in the medium, which will be the original amount minus the added sodium hydroxide divided by the total volume of the medium now, which is 25.00 plus 20.00. So, at this stage, what we observe is that the concentration of undissociated acetic acid in the medium would be 0.0055 molar. Now, from here we will also be able to calculate what is the concentration of acetate anions in the medium, which will be nothing but the amount of sodium hydroxide that has been added to the medium divided by the total volume of the medium now, and this turns out to be 0.022 molar. So, with the acetic acid, undissociated and the acetate ion concentrations available to us, we will plug these in our equation of Ka, which is nothing but the hydronium ion concentration into acetate ion concentration divided by the undissociated acetic acid concentration. Now, when we do that, we know the Ka value, we know the acetate ion concentration and we know the acetic acid concentration. So, this will help us get the hydronium ion concentration, which will be equal to the K value into the undissociated acetic acid divided by the acetate ion concentration present in the medium. This solves out to be 4.33 into 10 power of minus 6 molar, and from here the pH value can be calculated, and the pH has already risen to 5.364. So, at the beginning of titration the pH was, at the beginning of titration the pH was 3.0203, and even after incomplete addition of sodium hydroxide, the pH has already increased to 5.364. Now, let us see what happens as we keep adding sodium hydroxide into this medium. So, at equivalence point, so let us see a third condition, which is going to be at equivalence point. At equivalence point, that is at 25.00 ml sodium hydroxide addition, we will have all acetic acid has been converted to acetate anions, and the pH of the medium will now be dependent upon what is first the concentration of acetate anions, which will be nothing but 25 into 0.05 divided by total now 50.00 ml, and this then solves to the concentration of acetate anions being equal to 0.025 molar, because the volume is doubled, the concentration is halved. Now, one equilibrium to be considered here is when we have acetate anions present, they can also take up protons from water and convert back to acetic acid and produce hydroxyl ions here, and what we believe is that the acetic acid concentration is equal to the hydroxyl ion concentration. That is what the equivalence point will have. So, we can write a Kb value, which is nothing but the undissociated acid into the hydroxyl ion concentration divided by the acetate ion. So, this equation will give the Kb value for us, and as we have already seen that the acetic acid concentration and the hydroxyl ion concentration are the same. So, we can write this as Kb is equal to hydroxyl ion concentration squared divided by acetate ion concentration. Now, as we solve this, what we get is that the hydroxyl ion concentration is nothing but square root of the Kb into the concentration of acetate anions, and the Kb value can be calculated as Kw by Ka into the acetate anion concentration, and the Kw value is 10 to the power of minus 14. Ka value we know for acetic acid is 1.75 into 10 to the power of minus 5, and the acetate anion concentration that we calculated here was 0.025 molar. Now, when we resolve this, what we get is that the hydroxyl ion concentration turns out to be 0.378 into 10 to the power of minus 5. In other words, the pOH value for this system now comes to be 4.578, and the pH value will be 14.00 minus 4.578, which is close to 9.422. So, it is important to note here that the pH at the equivalence point for this medium or this system is quite basic. So, we should be able to use say phenolphthalein as our indicator in this case, and at equivalence point the pH value turns out to be 9.422. Let us see what happens when we add a little further of sodium hydroxide to this solution. So, let us take a condition where we have added 25.10 ml of sodium hydroxide to this titration. Now, when we have added excess of sodium hydroxide, what we have is that all free acetic acid is converted to acetate anions, and we have a little excess of sodium hydroxide which is present in the medium. Now, under these cases, the excess sodium hydroxide concentration would be nothing but 0.10 ml into 0.05 molar sodium hydroxide that has been added, divided by the total volume, which is 25.00 plus 25.10 ml that has been added, and this solves out to be almost equivalent to 0.0001 molar NaOH which is present. Now, when we have this concentration of hydroxyl anions present, we have the pOH value of 4.00, and hence pH value is equal to 14.00 minus 4.00, which is nothing but 10. So, of course, as we add a little excess of sodium hydroxide, the pH increases and becomes even more basic. So, we have seen how a variety of volumetric titrations or pH metric titrations are undertaken. Now, in the rest part of this week, we will be focusing on how we can use gravimetric titrations for our analysis, and we will understand what are the principles involved in gravimetric titrations.